Hi guys, welcome to my 13th episode of Love the Byte series. My name is Samuel Kamochu. I'm a telecoms and a software engineer. I'm the co-founder and the lead setter at Meliora Technologies. This is a bonus video. So in case you have not watched episode 12, please pause and go back and watch that episode because you might not understand some of the things we'll be discussing here. So my objective of this video is to highlight the use cases of Bitwise operations in the life of a software engineer. So the agenda is to look at 5 cases. The first one is to decode a flag. When you're dealing with protocols, you'll hear there is a certain flag. Extract a subset of bits. You'll find that in some cases you have a few bits that represent certain data, less than a byte. Dealing with unsigned bytes, we'll also look at how given 2 bytes, you can get an unsigned integer, or when you're given 4 bytes, you can get an unsigned long. So on to my first case, which is decoding a flag. So in this case, we'll consider a protocol called the diameter protocol, and we will consider 1 byte, which carries a lot of flags, 8 flags to be specific, in our Wireshark trace. Wireshark is a tool that you're able to view the trace or basically a series of bytes. You can decode them using Wireshark. So in this case, we have our message already decoded for us, but the byte in question is 40 and it has 8 flags. The first bit represents the request flag. If it is 1, it's a request. If it is 0, it's an answer. Bit 2 is proxiable, 3 is error, and 4 is potentially retransmitted. And bit 5 to 8, they are reserved. Please note, we are looking at the bit starting with the leftmost bit or the most significant bit. So don't worry about diameter. When we get to the third part of this series, you'll be able to understand more about diameter. Now that we know that our byte that contains the flag has 40 in hexadecimal, and we represent this in binary, it's 0100, because you know that when 1 is set, this nibble here, when 1 is set, it means it's a 4. And then of course the rest of the bits are 0 to representing the second nibble. Now, how do you extract a subset of bits in a value? E.g., we want to know whether the first bit is 1 or 0. Of course, with our naked eyes, we can see this, but how do you do this using a program? And this is where bit masking comes into play. So a mask defines which bits you want to keep and which ones you want to clear or ignore. So in the event we want to focus on bit 1 to the left, so you can actually create a mask to do that. So in this case, we look at the first bit, and the question is the above diameter message a request or an answer? And the hint is we have to analyze bit 1, which is from the left, if that is a request flag. So what you're going to do is, we know our value is this, and our mask will become this. And using the mask, we are interested in keeping only this bit and we clear the rest. And using the mask, if we do bitwise and, we know that all the 7 bits will be set to 0 because these are zeros. And the only bit that can take value 1 or 0 is the first bit starting with the left. So it will become 0 if bit 1 is 0, because 0 and 1 gives us 0. Or it can be 1 when bit 1 is set to 1. So in case this value is set to 1, it will be 1 and 1, which gives us 1. And that means it's a request. Otherwise, it's an answer. So you can see how you can use bitwise operation with the masks to actually determine whether a bit is set or not. So in this case, how do you check if a flag is set to 1? Or here we can say true. So the idea is we take the value, as we've seen here, we AND it to the mask, and if they're equal to the mask, just like you can see here, these and the mask are the same, it means that the bit in question was actually 1. Or if it is not equals to 0, again, we can use that to know that the bit is set. Now, if you want to check if the flag is set to 0 or it's false, request is false, meaning is an answer, we can actually do the value and the mask. And if the answer is 0, it means that the bit in question is actually set to 0. So everything else becomes 0, and that means that there was no match. So let's look at that in code. So one thing that I'd like to clarify is that anytime you see OX, it means that that number is hexadecimal. OB means that that number is binary. So in the event you have OX, the 2, 3, it means the 2 and 3, they're hexadecimal digits. And of course, binary, it will only be OB, 1, zeros, and just a series of ones and zeros. So in this case, the diameter credit control flag as flags byte, as we looked at, and here we know the order of the bytes. The first up to the fourth one, they have a meaning, and 5th to 8th, they are reserved. So our DCC flag is as we've indicated. If we convert to binary, it looks like that. Now, here we have the mask. Remember, the first bit, the OB, is not part of the bits. So it's just indicating it's a binary number. So we take the first bit and set it to 1, and the rest we set them to 8 to be the mask to be used to check whether the first bit, which represents the request, whether it is set or not. And for you to check the second bit, which is proxiable, we now set OB01. And if you want to check the third bit, then you set OB001. Then the rest you set them to 0. So you can see how we have the 3 masks. And you have seen if the request flag is set to true, all you need to do is to take the DCC flag, you AND it with a mask. And if it is not equals to 0, it means the bit was set to 1. I hope that makes sense. If it doesn't make sense, please reach out to me in comments and I can probably clarify the same. The same case applies to proxiable and this. And so when I run this program with my byte, which is 40, I get false, true, false, because the second bit will give us a true proxiable. The first bit will give us a false, it's not a request. And the third bit will give us a 0, meaning that it's not an error message. So, and you can see how Wireshark already decoded that for us, where we have it's not a request, it's proxiable, and it's not an error. So that takes us to the end of the first part. So the second part, how do you extract a subset of bits? Not a flag now, but a subset of bits and make sense out of them. And I'll use the IP header, Internet Protocol, another protocol. And Internet Protocol, the IP header, the first byte, the first 8 bits, they represent 2 different parameters. The first 4 bits represent the version, and the next 4 bits represent the header in words. Don't worry about words, we'll clarify that. So we know from Wireshark that the version is 4, and for you guys who can do the computations easily, this is a 4. 1s, 2s, 4s, this is a 4. 1s, 2s, 4s, 4 and a 1, that's a 5. But remember, the word is in IP specification, a word represents 4 bytes. So if you're looking at the total number of bytes, it's 5 times 4, which gives us 20. That's why you can see Wireshark decoding it as 5 into bracket, but the real answer is 20 bytes are used for the IP header. So let's do this in code. So you have the binary values 4, 5, and you have the representation of it. And once again, we use bit masking to rescue us. And let's extract the version. So we know the value to be that. The mask, remember the version is the 4 bits here. So we can use the mask. And we set the rest to 0 because we are not interested in the last part. Now, the next thing is we use the bitwise AND. If we AND the 2 values, definitely we get 0 and 1 becomes 0, 1, 1 becomes 1, and then the rest become 0. And that means this number, for us to get the final answer, we have to shift the bits to the right. Why? Because this number in itself, this is 1s, 2s, 4s, 8s, 16s, 32, 64. So this is in itself is 64, but we know the answer is 4. So we have to shift the bits to the right, 4 bits. So what will happen is these bits will move, each bit will move 4 steps forward, and that will definitely represent the 4 that we need. And we know that this is IP version 4. So this is one way, but the biggest question is, do you actually need bit masking? And we'll see that the answer is we don't need bit masking because we can just do the shifting alone. If you've done research on the shifting, then definitely this is not a foreign concept. But let's extract the header length part. So what we do is we take the value and we get a mask. Of course, we're interested in the last 4 parts and we're not interested with the others. Then we do bitwise and the answer will be that. Do we need to shift? No, we don't need to shift because the value is in the right place, and that gives us a 5, and that means it's 5 words, and this is equivalent to 20 bytes because 1 word is the same as 4 bytes. So let's look at the Java code representing this, just to illustrate what we have described. So the key idea is we look at the byte, it's 1 byte, version mask, binary, the first 4 bits are set, and then we come here and we take the IP header, we AND the version mask, and we get a byte that we typecast, because anytime you do this, it's treated as an integer computation. Then once we get the version, what we need to do is we take the version and we do bitwise shifting 4 to the right, and that will give us the answer as we had seen in the previous slide. And you can actually also do shift alone, and if you do this, if you look at line 13, the first line we got 4, which is correct, and we can also do shifting alone, and it will also give us the right answer 4. And then if you look at the header length, we use the mask for the header length, and then we come and do the masking. We don't need to shift, and once we print, we get a 5. But we know that the header length, those are words, so if you multiply by 4, you get the bytes, and that essentially gives us 20. So that way you've been able to see how bitwise operations can be used to extract a set of bytes, and you get sense out of it. Like the IP header, we're able to tell the version using the bitwise operation shift, and we've also seen how we can get the header length using the mask. Now, dealing with unsigned integers. Here I look at IP address. You know that Java, all types are assigned. So here we have the destination address in IP header again. We have 4 bytes, and the 4 bytes, if you look at the hex dump here, or the hexadecimal dump, we have 330F B3A8. Each byte is treated as an unsigned value, as all of you know that the IP address, each section can take a value from 0 to 255 and separated by dots to make these what we see as the printable IP address. So this is something that I believe you are all familiar, because you know how an IP address looks like. So you have 51.15.211.168, all created from the 4 bytes. And this is essentially converting each of the hexadecimal value to unsigned integer. So let's see how this works. So if you look at the hex dump for the IP address, this is how it is. If you do 33, this is 51. If you do your conversion, you'll confirm that that conversion is correct. But now in Java, the problem is that the last part, which is A8, which is supposed to be 168, is represented as this. Now, if you do system.out.println the last part, instead of getting 168, you get -88. Because when we learned about data types, we saw that the byte in Java is a signed number, meaning that it comes from -128 to +127, and 168 is not in the range. So the 168, as those bits are set, is actually a negative number. And how do we know that? Because A is 10, so you have 1, 0, 1, 0. This is a 2, and this is an 8. This is one nibble. And then this is 8, this is the second nibble. Now, one thing that we know is that the first bit, when it is set to 1, it's a negative number. And if you check the 2's complement of 88, I can leave you to do it at your own pace. You'll discover that it's the same as this. So that's why it printed, the computer printed -88. But how do we overcome this? It's easy. You can overcome that by something that we tackled in the previous episode, but we're going to repeat it here. So all you can do is you can take that byte, which is, let's say here, byte 1, or it could be part 4. Then you AND it with a OX for FF. Remember, F is 15, F is 15. So this is the same as ANDing it with 8 bits that are set to 1. But remember, when you do this, this becomes integer computation. So the answer is actually 32-bit, because integers are 32-bit. So let's look at it and illustrate this. So you have our number, which was 8-bit, basically a byte, and that was equivalent to -88 using the 2's complement. Now, I want to XOR it with FF. Remember FF, this one is an integer, so it has so many zeros, and then F and F, 15 and 15 in hexadecimal. So if this is something you're not familiar with, please ensure that you watch all the episodes because they are very incremental. So if you do and here, then definitely every place there is a 1, it will be reserved. Every place there is a 1, it will be reserved, and this one will be reserved. So essentially what we've done is we've created a new number with so many zeros preceding our original number, and the bit to the left, which is normally used to represent the sign, is set to 0, meaning that this number is positive. And if you look at this bit, it's 128 plus 32 plus 8. If you add all of them, they give you 168. And that's how we've been able to convert a byte, which was signed, into an integer that was not signed. And that way we're able to get the last part of the IP address. So there is also a second option. This is solution 2. Apologies for calling it solution 1. But Java has an inbuilt function, so you don't need to do the bitwise operations. You can actually do byte 2 unsigned int, and you pass the byte, and it is going to return an integer. In this case, it will be 168. So let's look at these in code. So you have 33, you don't need to typecast it. 33 is 51, 51 is within the range. 0f is 15, 15 is within the range. And then D3, this one is a negative number. So when you declare the JVM or the editor requires that you typecast into a byte. And A8, the same case, because they're out of range of the byte values. So if you print them directly on line 9, so you see that 51 is okay, 15 is okay, negative 45 and negative 88. We don't have IP addresses that have negative. So this is why we needed to do the AND with OXFF so that the number becomes this way. The second byte the same way, the third byte and the fourth byte. You can see now we've added a lot of bits, 24 bits in front of our 8 bits, and all of them are set to 0, making the number positive. And now if you do the computation, you'll actually get the correct answer, 51.15.211.168. And this is printed by line 15. Now the alternative is to use the inbuilt method so that you don't use the bitwise operations, and you can see that even using the to unsigned int gives us the same value as that. That way you've been able to do now decoding the IP part of the IP header. Please note, when you are a programmer, this data comes through the network interface. It is a series or an array of bytes. So you have to actually do this to be able to make sense of the 4 bytes. So you need to know where to start and where to end. And this is where the protocol specification document comes into play. Now let's look at case 4. We are combining 2 bytes into unsigned integer, unlike the other one where we had 1 byte to unsigned integer. So this one is a bit slightly complex because we have 2 bytes, but we have to put them together. So we know the answer is 384. This is total length, but the bytes are 0180. So when we look at it, the first byte is 01, represented in hexadecimal in Java, OX01. Second, and you know the answer is the O. First nibble is 0, everything is set to 0. The second nibble is 1, 0001. That gives us a 1. Now, the second byte has 2 nibbles, 8 and 0. And you know the first one is 8. You know this is 1s, 2s, 4s, 8. And then, of course, this will be 0 because it's set to 0. Now, with these 2, to avoid the problem of 2's complement, we are going to use integers, an integer with 4 bytes to combine the 2 bits, so that we have a preceding 16 bits, which will always have zeros, and our number will always become positive. And that way, you create an unsigned number. So let's look at a length. If I do int length, without me knowing what I am doing, basically behind the scenes, we have 32 bits reserved for us in memory. And if I do int length, then I OR it. This is an underline to highlight. I do the bitwise OR with the first byte. What I get is this. So I'll take this and then I get all these values. If you OR them, then wherever there is a 1, it is preserved. Wherever there is a 0, we have a 0. In that way, we've been able to move this number into the result or the length. Now, once we do that, we are going to shift the bits 8 times. So what you're going to do is you're going to shift the bits. Each bit will shift to the right. So this bit will disappear together with all these bits up to there. And then these ones will move 8. And of course, this one will come here. And the 1 will come to this position here. And then, of course, the 8 bits that are now to the right, they're actually set to 0. Please note that these bits will be set to 0 once we shift to 8. Then finally, we come and now we OR this. Remember, we've already shifted. Then we take byte 2 and we come here and we put it down there. Then we OR it. And what you can see is now a number that has the first byte and the second byte. Please note, these was 2 variables, but we've been able to combine them into one variable called length. So in other words, you have an integer length, which is made up of the 2 bytes. And if you look at the value, we know that this is 128 and this is 256. When you add the 2, you actually get 384. And of course, the rest of the bits here, they are set to 0. So that way we know that the total length is actually 384 as indicated in the Wireshark trace as seen in the previous slide. So when you look at it in Java, we have the 2 bytes, definitely. This one you have to typecast it because remember the first bit is 1. And of course, that's a negative number using 2's complement. And then we can now come and do exactly as we've written in our code. Then we shift and then we do this. One of the things that you'll note here is that I have done X, you AND it with OXFF, especially when you know that the number is negative, but you can actually, to avoid errors, you need to do this even for this number to ensure that you have a code block that can work for all scenarios. So what I do is I AND it with OXFF. This converts this number into integer, 32-bit, and the last 8 bits are set to 1 and the 24 bits are set to 0. So that now when you're doing the OR, the work becomes much easier. Then of course this gives us the answer, which is 384. But if you are a very, very good developer, you don't need to write all these instructions. You can actually write one instruction with this. And actually to make it better, you can actually put AND this in both scenarios. So you ensure that you first convert it into 32-bit using the AND OXFF before you shift 8 bits. And this will ensure that even if this value is greater than 127, you won't have any unexpected behavior within your program. So of course, the most important thing is for you to play with this data. Just ensure that you practice so that you get better. Now, the last part is combining 4 bits into unsigned long. And here you can see there is another protocol. This is TCP header. And there is a parameter here, TCP option called timestamps. And the timestamp value is actually 4 bytes, as you can see. And you can see this number is 2.9 billion. And definitely it's bigger than an int because an int is less than 2.9 billion positive. So here we have to use a long, and that's why I've said unsigned long. So in Java, int data type has 4 bytes, as I have mentioned earlier. Then we have AE, they can be represented like this. And you can know that the first bit is set to 1, meaning that this is a negative number. But you know timestamp is a positive number. And you know 2's complement complication comes again here. So what you're going to do is we'll do something similar to what we did in the previous slide. But in this case, we will now look at how to work with a long number. So we look at the first byte, which is that, the second byte, which is that, the third byte, which is that, and lastly, the fourth byte, which is that. I've just realized these are not okay, but I hope you will not get confused. B1, B2, B3, B4. And then we have the timestamp, which we will set as 4 bytes. This is an integer. And of course, all of them will be set to 0. Then what you do is you take B1, you AND it with FF. This will make it a 32-bit number and take care of those unsigned parts. And then you shift 24 times. What you get is you basically shift this guy, bit that was supposed to be here. You shift it all the way to this. Please note, this is another way of it saying that timestamp is equals to timestamp or the value you get on this side. So you can actually say timestamp or equal then you do this. Don't worry about that. In case you have a challenge, you can go try this, and you can try the long approach. It will also give you the right answer. So I do the same now with B2. And now basically what will happen is these parameters will come here. We are using OR, and you must ensure that first you convert into this so that you don't get into one's complement complexity. And then we can come and do the third one, basically B3. And the idea is now to move these ones and zeros to the third position, the third byte. And then lastly, we have the last byte, which will move to this position. So at the end of the day, this is a negative number because of this. So in case you want to get the long, which is a timestamp, so you can say timestamp long is equals to integer.to unsigned long, and you provide the timestamp that was an integer. That way you'll get the correct answer. And in this case, in our example, we know that the answer is supposed to be 2.9 billion plus. So here we'll come and do the same. So if you look at it, I've declared the bytes as indicated in the dump. The idea is that this data will come through the network, so you don't need to write the bytes. You'll get the bytes from the network, and then you're supposed to decode these. We declare our timestamp, which is 00. This one you can just declare as 0, even without saying hexadecimal, or even OX00, it will still work. But I just put the 8 nibbles or 4 bytes just for illustration sake to ensure that the timestamp is 4 bytes. Then I come and do XOR. As I said, timestamp OR is equals to B is the same as saying timestamp is equals to timestamp OR B. So it's just a way of shortening the statement, which is supported in Java. And so I've used this to ensure that our lines become shorter. But the key thing is we AND with FF, then we shift each number. We shift 24 times so that we get it to the left byte. Then we shift B1 16, second left byte, then 8, that left byte, and then B4, which is index 3, then we get it to the right. So I hope this does not confuse you, and what you get is this number. But note, if you print this number, it becomes negative because we know that these values, the first bit, which is AE, has a 1 at the beginning. It makes it a negative number. And that's why we use now the integer to unsigned, and we get the timestamp at this one. But now I'm doing this because I know the bytes and I can pick each byte one at a time. But normally when you are programming, when you receive the byte array, you need to know the start and the end. And all you need to do is to ensure that you can use the follow to do the same. So I'll not take time to explain this, but I believe you guys can look at it. If you have any questions, please feel free to leave a comment, and probably we can do a video now to illustrate loops, or we can guide you to where you can learn more about loops. Yes, and that is the last case study. By now, I know you want to get the source code repository, but I'm not going to share the source code until we do the hackathon. I know you too well, and I hope this is okay with you. So why is this important? It's because the protocols govern digital communication. Right now, we mentioned TCP, IP, diameter. Yeah, those things govern digital communication. Binary protocols rule the world. So when you consider all these protocols, binary protocols rule the world of digital communication. But binary protocols, as we know them, there are no go zone for the African engineers or African engineers. So my responsibility is to ensure that we get more guys to play with these binary protocols. That's why we are calling it the series Love the Bytes and Protocols. Text-based protocols, unfortunately, they also use bytes. If you are a HTTP guy, or you use SIP, which is used for voice call or the voice over IP, they use bytes still. So you have to learn these things. So as I said earlier, this makes you a better engineer, and you need this stuff. And you've been surviving without this, you need to thank God. But please note that you cannot survive in the future without knowing these things. So another thing is, I think one of our members here, Brian, who is also part of the team, wrote an article, and I just thought of sharing this. The answers you seek are always available. This is under knowledge is power. Ensure that you read. The trick is finding them. There are resources all over the internet that can help you get an understanding of any concept. Having gone through each page of the HTTP RFC, I've realized that so much is abstracted by the frameworks we use every single day. So this is basically to tell you that these things are not complex, and if you know them, they make you a better guy. So I've come to the end of this video, and if you found the content interesting, or you think the content might be helpful to someone else, please share with them, and feel free to like, comment, and subscribe. And as always, please don't forget to turn that notification button. Thank you very much, and see you again in the next, should I say, episode or webinar. Thank you very much. See you again next time.